So it's my pleasure to have introduce Professor Debmalya Mandal. Debmalya is a faculty at University of Warwick. He was earlier a PhD student at Harvard with David Parks, and we are postdoc at Columbia and at National. So Debmalya works on various things of interest to us. He works mainly in the intersection of ML and socially interesting problems, things like information elicitation, fairness, and so on. He's worked in some game theory problems as well. And now today he's going to talk about performativity in reinforcement learning. As you mentioned, Debmalya is going to be around for a couple of weeks until next Thursday. He's in 207. So yeah, please feel free to stay a little bit.
Yes. Okay, sir. Yeah, thank you for coming to my talk and also for hosting me. So, what I've tried today is before going into reinforcement learning, I will try to motivate why we should think about like even classical supervised learning a bit differently. And so here is sort of the classical view of machine learning, which has been around for like 30 or 40 years. So you have data collected from some distribution, and you choose a hypothesis class, and then what you solve is this empirical risk minimization, which minimizes this empirical loss. So tries to find the best hypothesis in that class. And the main assumption here is that the data distribution D is fixed, or another assumption is that, okay, you are drawing data from some distribution, and once you deploy your model, it's being evaluated with respect to the same distribution. Okay, so now there are many settings where the data distribution is now static. So, okay, so here is one example. This comes from strategic classification. So suppose you are a bank and you want to decide who gets loan or not. And so based on the features of the applicants and past data, you decide a classifier. So here you have like two features, let's say. And so you say that, okay, so here is the decision boundary of the classifier. And if it's on this side, then your application is rejected, and here it's approved. Now, if you publicly announce this classifier, and what happens, and this is not just a draw example, but in many settings, what has been observed is that people that are close to this decision boundary, they can change their features. And so usually, okay, you can assume that people can manipulate their features to get better decisions, but that also has costs. So probably like, okay, like if someone has features here, then they don't want to change, but decision boundary, the features that are close to decision boundary can change. So effectively you get a new kind of decision boundary, which is not what you have started with. And yeah, so this is, for example, this has been observed in risk assessment and resource allocation, where you decide, okay, who gets which resource based on some features, and they're also some. And another example is, competitive marketplace, where, okay, so you have some past data of, let's say, okay, some price for some products or some inventory, and using that, if you build a model and announce a model, then your competitors might react to it, and you get very different results. Okay, so this is some examples of a couple of examples from supervised learning where the data distribution might change. And there are also examples of this kind of effects in sequential decision making. For example, in online platforms, they use reinforcement learning or some kind of bandits for recommending items, but it has been observed that it can cause preference amplification. So I have cited one paper which sort of details how preference amplification in Facebook recommender systems, and it can also have like polarizing effects. So there are both empirical and also some theoretical studies. So theoretically, what they say is that, okay, so if I recommend some item, so then it's usually there is some kind of word embedding, which is a vector. And people's preferences are represented by another vector. And if you recommend one vector, this item vector to this user vector, then based on this angle, so the preferences can change. So there are also some theoretical models to justify this kind of preference changes. And so this is the final example. So I'll talk a bit about probably later if I have some time. So this is about fine-tuning of language models. I don't know if you can say it, but yeah, so the first step in language model is pre-training, where you can think of like, okay, you build a large model based on like all data available on the internet, and that can just predict, that can generate reasonable sentences. But then the fine-tuning step usually uses reinforcement learning based on some human feedback so that it works on some particular data sets. And yeah, so we know that with this kind of reinforcement learning based recommendation or finding, it also has some impacts on preferences. This is probably with abstract example, but it will probably be clear later. So what I'm planning to do is first I will present a new framework based on mostly game theoretic insights. So that's not by my work, but some prior work on how should we think about this kind of setting in supervised learning, and then also some of our works on extending that for reinforcement. Okay, so this is called this framework that I'm going to present in, at least for supervised learning, it's called performative prediction. And okay, so this was the classical model. So you're given a model theta, and then the data distribution is D, and you want to find the best hypothesis that minimizes the loss. But now the framework presented in performative prediction by, I think, Juan Perdomo, Tiana Zerni, Tudor, and others. And so what the idea is that the distribution is no longer fixed, but if you have some model theta, then the distribution responds with respect after deploying the model theta. So now we have this parameterized class of distributions, and now the goal changes. So what you can say that, okay, one goal could be I want to find a stable solution, performatively stable solution. And the idea here is that suppose your data distribution is generated from this d theta s, and then this theta s actually minimizes the loss. So the idea here is that, okay, suppose I deploy this model theta s, and then the environment changes to d theta s. So you have new distribution. But now with respect to this new distribution, your model is optimal, so you don't want to change. So it's the stable point.
So yeah, what is this? Capital S?
Yeah, so I'm saying that theta is a stable. Yeah, it's a stable data.
Shouldn't that be d of theta in the argument?
No, it should be d of theta s. The reason is that if the distribution is d of theta s,
Yeah.
then your theta s is optimal.
Okay.
I think it's kind
This
of,
is not this is an implicit representation. It should satisfy this. It's not
Yeah.
an equality. It's not saying that x is equal to y. It's saying that should satisfy this equation.
so it's like one-sided Nash. You can think of.
Okay.
It's like a fixed point.
Yeah.
Okay.
So there is only one such theta S for this class of distribution.
Okay, so that depends on a lot of things like how the distribution responds or what. So it's not yet clear that such a solution exists.
But this is how you were defining
Yeah.
performance.
Actually,
You haven't.
you haven't told me what is D here. So for some D, I'm sure it is clear that such a solution exists.
Okay, so I can tell you, so if this loss function is convex in theta and t satisfies some kind of bounded sensitivity assumption. So if your theta changes little, then
Yeah, then
distribution.
Yeah.
So then you can use standard fixed point argument to put that such solutions. Okay, and they proposed a second concept which is called performatively optimal solution. So now it's just d theta. So now suppose you deploy theta, your model changed to d theta, then with respect to this change distribution, you want to optimize. Yes, and so if you know about Stackelberg equilibrium from game theory, so this is close to Stackelberg equilibrium and this is close to Nash. Okay, so yeah, so how do you find a stable solution? So they showed that if I just do repeated optimization, so you start with the model theta 1, distribution changes to d theta 1, then you optimize for this by collecting data from d theta 1 to get theta 2, and it changes again. Yeah, this should be. Yeah, maybe it's problem in the video or okay. Yeah, so this iterative process converges if what we saw is that the loss function is strongly convex and the distribution map is not too sensitive, meaning that so, yeah, distance between d theta and d theta prime is bounded by some constant times the distance between those two points.
And L is probably bounded also.
Yeah, I think
Otherwise,
so they
or
are
maybe the distance is with respect to L.
they assume strong convexity and
So let me say that earlier that like the point should be that now the expectation should also change a lot
yeah.
when you change theta.
Yeah, so they are bounded smoothness in L. I don't know.
Bounded smoothness. Oh, okay, so that's what those parameters are all play around with the epsilon.
Okay, yeah, and similar results hold for obtaining a performatively optimal solution. But I think what happens in performatively optimal solution, you cannot usually get this kind of last iterative convergence. So if you run your process for t steps, you can say, okay, one of these t steps is close to optimal solution. Okay, so I'll actually show a very like some brief sketch of idea of why this kind of repeated optimization works. So here, okay, so there are three loss functions. So L0 is the initial loss function, and you optimize, let's say, so this is your parameter theta 1. And then the distribution changes and you get a new loss function. This is L1. And you optimize to get theta 2. And in response to theta 2, this L2 gives a new loss function, you get theta 3 and so on. So this is the dynamics. And so roughly what you can show that, okay, using this bounded sensitivity assumption, the distance between L1 and L2. So L1 was in response to theta 1 and L2 in response to theta 2. So this is bounded by epsilon times the distance between these two. And yeah, so theta 2 and theta 3. So you are optimizing two strongly convex loss function. So, and if it is strongly convex with parameter mu, we can show that, okay, it's roughly over mu times the distance between this. So here it's important to have strong convexity because if it's just convex, then probably you can write down two convex functions that are very close, but their optimal solution might be different. So just increase the flatness of the function.
So can you just go back on that? So previous slide, we have just slide.
Yeah.
So what are L1 and L2? We still have a single loss function.
Yes, I think that's the point. So that L1 L2 is the expectation of the loss under T.
Yeah, so
And you need to have that the sensitivity, like low sensitivity for T.
Those are-
Carries over to low sensitivity for M.
and then expecting our
So that's what.
expectation.
That should be reasonably well behaved at the distribution that close the expectations are. Yeah.
Yeah, so L1 is the loss function because of model theta 1, and L2 is because of theta 2. Yeah. Yeah, so you can bound this to difference by the strong convexity parameter. And then basically you do rearrangement to show that okay, theta 2 minus theta 3 is bounded by some terms times theta 1 minus theta 2. And then, okay, you basically get a contraction mapping if epsilon mu satisfies certain properties. And then if you just iterate, then this process converges. Yes, and as I said before, you get last iterate convergence, and also this is linear kind of convergence. Okay, so now my goal is to extend this framework to reinforcement learning. And okay, so here is very quick summary of reinforcement learning. So I'll start with tabular entity. So you have state, action, reward, and transition. So tabular means that number of states are finite, number of actions are finite. And okay, so reward is a bounded reward between 0 and 1, and you have probability transition. Okay. And the goal in reinforcement learning that you want to maximize value function. So in this talk, I will assume that the goal is to maximize this geometrically discounted sum of reward with parameter gamma. And yeah, so if you restrict to some policy class, then you can try to find the optimal policy that maximizes the value function. So this is the goal in standard R. So I'm not assuming like anything changes. And so what we propose, so the framework here is that the policy phi changes the underlying MDP, basically. So that's the framework we propose. So in standard RL, so we have this learner phi, so that interacts with the environment. And okay, so learner takes some action, the environment, suppose this is fixed and gives back the reward and next is and continues. But here, what we are assuming is that there is some kind of environment mapping that gives you back the new transition and reward. So roughly the idea is that now instead of just one MDP, so the MDPs are parameterized by policies. So in the context of supervised learning, so the distributions are parameterized by models, but now these MDPs are parameterized by policies. And yeah, I'll be assuming state and action are fixed, but this reward and transition are changing. Okay, so now, yeah, so you can define something called performative value function. And it might look a bit confusing, but the idea here is that, so I'll write phi superscript phi and subscript phi prime. So this subscript means the underlying MDP is M sub phi prime. And the superscript is the policy that you have deployed. So if you deploy your policy phi in an MDP M phi prime, so this is the value function. This is the sum of returns. Okay. Yeah, so this expected return under policy phi with the underlying entities M phi prime. Okay, so
And AT is an action from the state. So if your policy changes, like if so, you said like the policy may change and the reward cannot depend on the policy. Right? So if you take the same action AT, then when your policy changes, you get a different reward, or if you
yeah, so what we are, the model is like you can think of like in terms of stages. So if it's one policy phi, and then the MDP changes to M phi, so then you interact with this fixed policy. You collect some trajectories or get some rewards. And then after some time you update the policy, then the MDP changes. That's the model.
yes, but suppose like you update the policy and you take the same action.
Yes, then you get a new different reward.
Different reward here.
So yes, I think yeah, I have heard like people say that okay, maybe this model is too strict. Like if you change policy locally, then probably the whole environment should be changed. But yeah, so this is like first kind of modeling, so there's you can propose some other models.
So can you think of a mixture of policies that that's just a new policy? Like what was-
Yeah, so the policy can be anything. Okay, so yeah, so we can similarly define a performatively stable policy. The idea here is that, okay, so if the underlying MTP is M pi sub S, then your pi sub S maximizes the L function. It's very similar to performative stable solution in prediction. And then the performatively optimal policy is that, okay, you deploy pi, MTP changes in one step to M pi, then with respect to this changed MTP, your policy is optimal. Okay, so now, yeah, so there are now two questions. So one is, when does a performatively stable policy exist? And the second question is, how can you find it? Can we extend this kind of repeated optimization that I showed earlier for supervised learning context? Can you extend those ideas here? Okay. Yeah, so when does a performatively stable policy exist? So the problem is that the value function is usually non-convex in policies. So this is true for like different kinds of policy representations. So there are like softmax policy representation, also representation, but for most of them it's non-convex. So yes, even if you assume that, okay, the environment has bounded sensitivity, you cannot get a fixed one. You can come up with examples of where this kind of stable solution does not exist. So what do we look? So for this reason, when you look into something called an occupancy measure, so I'll define it in the next slide. But what happens is value function is usually linear in occupancy. So then you can try to find stable point in terms of occupancy measure rather than in the policy space.
But for a given occupancy measure, there might not be a policy.
So yeah, so you can normalize the occupancy measure to get a policy. And okay, so
In the limit. So occupancy measure would be like about like roughly like some kind of stationary.
yeah, so let me define maybe. Yeah, so this occupancy measure is long-term discounted visits to state an action. So yeah, so I have written D by prime, but for a moment you can also ignore this pi sub prime. So this is actually over the long term, what's the discounted average of visiting status and state action rate? So that's the measure for state S and action rate. And we'll roughly try to find, okay, so it will be clear on what I'm trying to do. So let's rewrite the condition for a stable policy in terms of occupancy measure. And so this is the value function. So if the underlying MTP is fixed as D sub S, then so this is the linear, it's a linear in D and reward. So this is the value function. And now we have this additional constant. So this is usually known as relevant flow conditions. Or I can write it here. Yeah, I mean, this is just standard condition. If you haven't seen it before, so this equals some initial.
So this for the field which is in the policy, it's allowed to depend upon time. Like if I see a certain state at a given time, I can.
Oh, okay. So we are actually stationary policy.
And still you can take any occupancy measure and get a policy.
Yeah, so you can normalize the occupancy measure. So one definition is you can define something like this. So if I give you an vector that satisfies this kind of relevant flow condition, you can define this. If this denominator is positive, otherwise you can define arbitrarily.
This would have the same occupancy.
So in the stable MDP, so if I define again, let's say I have MS, that's a stable MDP, and I find the occupancy measure DS, then I can get the corresponding policy.
And this would have the
Same occupancy measure. Okay, and the reason we are doing this, now this objective becomes linear, and also you have linear constraints. So now you can show that you can use standard fixed point arguments to show that there is a fixed point. So this is one way to avoid non-convexity, but I'll probably mention another way towards the end. Okay, yeah, so the goal is to find such kind of stable solution in occupancy measure space. Okay. So we'll do again repeated optimization, but so in the supervised learning setting, you wanted a loss function that's strongly convex, but it's just linear. So one standard way is just you add a regularization to make this strongly concave. And yeah, so that's what we'll do. But the point here is that if I add a regularization, then the fixed point changes. Now it depends on this regularization strength lambda, so that's why I'm writing G lambda S. And we'll try to first find this fixed point of this problem, and then choose lambda to get some kind of approximation. Okay, so basically you solve this optimization problem. So at time step t, so I declare this, I have this occupancy measure, let's say t star t. Then I find the corresponding policy, I deploy it, and then the environment changes. So now you can solve this optimization problem. It's like a standard error problem. So and then you get a leaf occupancy measure, and you continue with this.
Sorry, could you just say a sentence about what is the idea of regularization?
Yeah, so in supervised learning setting, so what they showed is that this repeated optimization converges if the loss function has to be strongly convex.
Okay.
If it's convex, then it might actually be hard, very similar to very hard, but I haven't seen any hardness result. So now I also want like something similar to like this repeated optimization. So that's why I'm adding this regularization. So that makes this objective function strongly concave, not because we are maximizing.
Your lambda could possibly be very large.
Yeah, so yeah, I'll come back to it later. So you have to choose lambda so that you can get how close to the true stable point. Okay, yeah, so this one I already explained, and what you are trying to do is, okay, so you have, let's say, time step t, this occupancy measure dt, and I deploy a policy corresponding to this, then the MDP changes, and you again optimize to get new occupancy measure dt plus 1, and this method continues. Okay, so yeah, so we need for convergence, we need very similar bounded sensitivity assumption that the UR function doesn't change too much, and the probability transition also doesn't change too much. And yes, I'll denote by epsilon sub r and epsilon sub p these two conditions. Okay. Okay, so let me state the theorem. Yeah, so what you showed that if lambda is larger than some threshold, that depends on this sensitivity epsilon r and epsilon p, plus some additional constants that depend on the size of the state space, the number of actions, and discount factor gamma, then you get a very similar convergence. I'll briefly mention a few ideas about how to prove it, but let me just state the results first. So now, okay, so because I added this regularizer to make the loss function strongly concave, so I'm converging to d lambda s, but not to the ds, which is unregularized stable policy. The stable policy with respect to just the linear function. Yeah, so but what you can do is choose lambda appropriately above this threshold, so that you can actually show that the error is this much. So you can get approximate stable that depends on this constants epsilon r and epsilon p. And yeah, so the point is that if both of these two converges to zero, then you're basically getting standard error setting, and this stable point converges to standard optimal policy.
Usually optimization problem is used.
It just, yeah, it's a convex optimization.
Okay, so even if epsilon r, epsilon p tend to zero, that just means that you have one simple MVG.
Like it's a bounded error from zero, then there is still some effects of your policies.
Right, but even in the single MVG case, I mean, like you're saying that it's not a convex function with regard to the policy, right? Even for a
Yeah, or with respect to policies.
So then how do you show that,
But it's the parameter range with D, right? So
Yeah,
we just forget about the policy. There's a D, and D and pi there's a one-to-one map.
it's,
But yes, there is one difference with respect to the proof for this supervised learning setting. Yeah, I will mention. Yeah, so here are some simulation results. Yeah, so this is very simple setting. So this is a grid. Okay, so this is a two-agent environment, and the goal of one agent is to go from one of these start states chosen from at random to this goal state. And the second agent is basically adversarial in nature and places these blocks in the grid. And these blocks have different costs. So the exact setting is not that important, but the framework is the following. So the first agent, the agent that wants to go from S to G, plays a policy pi1. And the second agent in response chooses an approximately optimal policy. And yeah, so what I mean by approximately optimal, the second agent computes optimal Q function and then chooses the policy pi proportional to this Q function, but with parameter let's say beta. And you can show that for this kind of setting, the sensitivity you can bound by beta times polynomial k divided by 1 minus gamma squared. So one important fact is that it's independent of the size of the state space. But yeah, so how much, basically how approximate the second agent follows, it determines the sensitivity parameter. So if the second agent follows exact optimal, then it becomes like finding a Stackelberg kind of problem in general MTP image interval, which is actually hard for people. Okay, yes, this is so there are two simulation results, very simple setting. So this is when you exactly know the model after deployment, how it changes. And you can show that, yes, if the sensitivity parameter is like too large, then you cannot get convergence, but if it's small, then you get convergence. And the second one, where you don't actually see the new environment, but you collect some data and then solve the planning problem each step and then solve a new problem. And roughly how many samples you get, that determines how close you can go to the stable solution. Okay, so here is so I'll just mention how it differs from the supervised learning setting. So we are solving this problem repeatedly, and the framework is you deploy this policy corresponding to DT, then you have empty M sub t, you solve again to get D sub t plus 1 and continue. Okay, so because we added this regularization, the objective function is strongly concave. But the problem now is that, so we have this constraint set that changes with time. So, for example, it could happen is that D sub t is not in the constant at, let's say, time t plus 1 and so on. So the main idea that we used in supervised learning is that, okay, so if you optimize too close from the convex loss function, then their minimas are also close. But here, because you are optimizing a constant objective, it could be that one optima is not present in the constant set.
But this also is continuously seen.
Yeah.
Like this constant set is itself, like
Yeah, so you
linear
can-
constraint itself moving continuous. It's a polytope which is deforming and continuous.
Yeah, but now it's because you're polytope, it's hard to ensure like where your optimal point is. Now you have that.
Yes, but everything is continuous still. I mean, the point will move. So
Yeah, so maybe you can prove in this way, but
yeah,
the way I saw this is actually quite easy.
yeah, or
So you just write down the dual of this optimization problem. And what you can show is that in the dual, it's constant, but the constant don't change in the dual problem.
but the fun side is
Yeah, the function will change,
yeah.
but the objective changes in the dual. The dual actually has strongly convex objectives,
Well, yeah.
but the constant don't change with time. So now you can use the very same idea like in supervised learning to show that okay, this sequence of dual optimal solution converges. And now because this is a convex optimization problem from duality, to show that okay, if it converges to some stable solution, this primal optimal solution also converges. That's the idea. Okay, so yeah, so we can extend some of these ideas beyond tabular MDP. So the tabular MDP is a class of MDPs where you're assuming okay, state space is finite, action is finite, and you want, let's say, sample complexity or optimization complexity to be polynomial in states and actions. But for large scale MDP, so there have been like several proposals of how to model large scale MDP. And so one of the first one was, or actually the tractable one. By tractable, I mean you can get both efficient learning and efficient planning together in this linear MDP model. So in linear MDPs, the idea is that there exists some d-dimensional features, DIM, so that the reward is linear in the features with some parameter theta. And the probability transition is again linear in these features with some measure mu. So now this measure can be signed measure. Sign means it can have both positive and negative. And yeah, so what we try to do is extend some of these ideas for this linear MDP setting. And yeah, so what you want is this kind of approximation to stable solution or sample complexity. They should be polynomial in the dimension, this sensitivity parameter and 1 over delta. So delta is how close we want to be. But it should be independent of the state space, which now can be like infinite or very large.
Thank you, sir. This was in the tabular MDP case. How is the problem presented to you? Like, are you given? Yes, that's what you were saying about this thinking. As in, like, for each theta, are you given, or for each policy, are you given what the eight eyes and the?
Okay, so
what's just the?
yeah, so initial. I think yes, the first result was okay, you deploy policy, you get to know exactly, let's say, what R pi and P pi is. Okay. So then you can solve the planning problem and you get a new policy.
So you see, at each iterate, you get to know what the.
Yeah, so that's one version, and then you can also consider a finite sample version where you don't exactly get R pi or P pi. But with respect to the new MDP, you get some trajectories or some sample.
I see.
So now you have to determine okay, how many samples do I need at each iteration picked from bios. Okay, and yeah, so here we also, yeah, I'll just mention the results. I can discuss them offline if you're interested how to put them. So yeah, so suppose bounded sensitivity holds and this lambda is larger than some constants depending on this sensitivity parameter, and here you have square root of dimension instead of state space. And additional parameter, it depends like how the features span in this d-dimensional space. And yeah, so now again you can choose lambda appropriately to get convergence, approximate stability. Yeah, I think this is just 1 minus gamma square factor 6. And I'll also mention the finite sample bound. So what it proved is you can get per round sample complexity that's polynomial in the dimension. And it's lambda 4, I think lambda is this value, you know, substitute. So roughly, okay, that's some dimensional power segment, but it's still polynomial. And so this is per round sample complexity, and for converging up to error delta, but you get linear rate of convergence. So the number of iterations you need log 1 over delta. So yeah, if you multiply this by log 1 over delta, this is the total sample complexity. And in each iteration also, we use some kind of parallel dual ideas. So solving this planning problem with finite samples is also efficient. Okay, so
Maybe it's closer to Instructor.
yeah,
Yeah.
So we can restart this.
Yeah, so it should be on the test, I think. Okay. So if you want sound, you want to hear sound.
Yes. Yeah.
You should go.
yeah. Yeah, this is
I think we should limit of.
I think we click on more there.
More and eight maybe.
There's a more of this.
No, just click on it and.
Hide floating video. Yeah. So this coverage evolution is what is the way of kind of like
so
like smaller.
coverage conditions. Okay. So this is quite standard in offline reinforcement learning. So the idea here is that suppose you collect some data, like think of standard reinforcement learning. You collect some data and you want to learn the optimal policy from this data.
Yeah.
So if the data doesn't have any, let's say it doesn't cover any,
So every state action is seen.
no, does not have. So it needs to cover, let's say at each state, the optimal action is something taken by some optimal policy. The data must cover those actions
So the best action should show up in the
with some probability.
with high probability. It's an assumption on the.
So this is called single policy coverage or single policy.
But it's an assumption on what? It's an assumption on the sampling on the
It's the assumption on the underlying
P or
model actually. So here the assumption in particular is that if you deploy some phi t, let's say, and then the environment changes and you have new optimal policy, then you need coverage between phi t and this phi star of this new environment.
But is there a way to write this condition without referring to phi star, like just in terms of state space? That's probably bad.
You can probably write something
Will it be too strong?
in terms of features like this. Yeah, but I haven't processed it. Yeah, but I know like in offline RL, this kind of assumptions are this. Okay.
But is there also a condition the kind of variance that if the data, like after the fact, if the data had the property, then condition on that the probability of the confidence. So you collected some data, which is a random sample, and it turned out that it was like, so you don't know whether it covered or not, but if it explored every action, then condition on that event, your confidence is high. Is that the kind of guarantee?
No, we just assume that okay, you have this kind of coverage.
Okay. And it's a high probability event.
Yeah. But I think there are some other results where you can show that the guarantee then it would be if you have partial coverage, then your like the suboptimality gap will also have some kind of divergence between partial and your sample policy. So you have this two terms. Yeah. Okay, so yeah, a couple of ongoing work that yeah, I'm also working at the moment and happy to chat more. So one is I mainly talked about computation of stable policy. So there is I don't think many work on computational performatively optimal policy, both in supervised learning and also in RL. So there are a couple of papers, but not much. And yeah, so multiplayer setting is an interesting extension. So instead of one learner, if you have multiple learners. But what happens in multiplayer setting is this obtaining this kind of last iterate convergence is hard. That same thing is like last iterate convergence for Nash is also very hard for multiplayer setting. And yeah, so what I mean by here, consider a parametric class of policies. So what I said is that okay, it's a non-convex functional policy, so you move to occupancy measure. But you can try to find some kind of local stable point in occupancy measure. So what I mean by local stable point is okay, so your value function is non-convex. So let's say so you cannot probably obtain this kind of solution at max. So this might not exist because value function is not convex, but you can get local kind of stable points. So local means that you can have this gradient is zero. This is zero at so you can actually show that even though the function is not convex, this kind of solution actually exists. So yeah, so if you want to find, let's say you fix some kind of policy class, and if you want directly to find some kind of local stable point in that policy class, that's also quite interesting. Okay. And yes, we presented one paper where we consider the setting where the environment doesn't adapt immediately, but it takes some time to adapt. And so their repeated optimization might be slow. And so what we propose is this new method called MDRR, which is mixed data repeated retraining. So what you do is you wait for some time so that the environment stabilizes because it doesn't change immediately. And roughly, you take data from this past episode in some geometrically decreasing weights, and then do repeated optimization with this mixed weights. So yeah, so here, this is like empirical result, but we also have some theory. Like this mixed kind of repeated retraining can have faster convergence if the environment adapts. Okay. And yes, that's what I wanted to present about performativity in RL. I will mention one work in RLHF next. But if you have any question about this part, then one or two questions I can take for. Or later.
I mean, this occupancy measure, this is a fairly standard idea. Yeah, this is used in like what are the other kind of problems where this comes up? Like this would be
So this has been coming up recently because so in linear LTP, we want to find, let's say, optimal policy from offline data. And there is often representation is used because of linear programming, there are a lot of parallel dual methods, and those methods seem to give like optimal sample complexity funds. It's there. But okay, so it's not clear how you generalize those kind of algorithms for slightly more general models. Like if it's slightly non-linear or even like quadratic model, just like that.
Also, in a simpler setting, in like very classical theory of smart functions, is like one way of defining a condition. Sure, we just say what fraction of the time you use the escape, and then ensure that it's stationary.
But here there is also a discount factor.
Yeah, here is the discount. Here is the discount.
So because of the occupancy measure, you can convert this non-convex problem into an LP.
Yeah.
Into an LP, then
It's not, it's a linear objective, so that's why you get the stable part.
I mean, you also have this condition, so these are also linear.
Yeah. Yeah, I mean, otherwise, I'm not sure how you can use fixed point theorems to prove the existence of that's.
Also, in that case, you don't really, I mean, it's just copy converted. You don't, you really need anything, in the, even in the original. Like, I mean, the thing is that the distance are decreasing. So it's not even, it's like just copy convergence. Yeah. And so that's just completeness. So there's no contraction as such. I mean,
No, but you give rate.
you need, yeah, but that is good because it's growing, becoming smaller. So it's a quality sequence, and therefore it has to converge. That's
Yeah.
so like it's already the proof of the fixed point theorem is embedded in the.
Yeah, and another thing is, yeah, some of these results could be hard, like if you just have, let's say, convex function, that's not much down the convex. And here also, like obtaining very close to stable point, but I think those hardness results also.
Yeah, that's right. So it's not known what happens if you drop the regulator. Like, do you know that it is?
So
It's
it's
it will not happen, or
Yeah, so in the original paper, what they say that okay, if you just have convex function, you add regularization to be strongly convex.
okay, but if you can analyze it already, that's open.
Yeah, the hardness results are mostly. Okay, so I have 2 or 3 slides about RLHF which I have been working on recently. Okay, so how many of you have seen this slide?
On paper, right? It's directly from there, right?
Yeah. So this is like one of the most overused slides which represents what RLHF is.
I think I've seen one picture.
Yeah. Yeah, I took the whole picture.
Different.
Okay, so what it says that okay, there are roughly 3 steps by which language models are fine-tuned. The first step is supervised fine-tuning. So it says that okay, so I give a base model and ask this question. So explain the moon landing to a 6-year-old, and then people give some text completions, and just like standard supervised learning, you fine-tune it. So that's the first step. And then the second step 2 and 3 is actually RLHF. And here you collect, instead of this text data, you collect comparison data. So it's the same question, like 4 choices. Then a human developer comes and ranks them. And then you learn a reward model that fits this rank. So if I say that okay, D is more preferred to C, then reward for D, given this prompt is larger than reward for C. So once you have this reward model, then basically think of this language model as a reinforcement learning problem, where you have this, okay, the reward for taking this action for this prompt is given by this learning reward model, and it will optimize. So that's basically the RLHF pipeline. So I think, so this is from this Instruct GPT paper, which was the version between GPT-3 and ChatGPT.
Yeah, Instructor.
Yes, this paper, yeah, so it's like GPT 3.5.
Is it the old paper of Christian or Cal?
Yes, I will mention it in the next slide.
No.
Yeah, so yes, the original paper was by Paul Christian and others. This deep reinforcement learning from human feedback. And yeah, I will also explain just one step model, not the multi-step, for which now it becomes just contextual bandit, not even an RL. So, okay, so you are given a prompt X and you have 2 possible completions, Y1 and Y2, drawn from this supervised fine-tuning model. And the experts give preferences between these two, yeah, according to this logistic model. And some true reward model are star. And yeah, the RLHF usually has two steps. The first is reward modeling. You're fitting a reward model that maximizes the likelihood or minimizes the likelihood according to this preference model. So you get this reward model, and the next step is policy optimization. So you optimize the value function. So this is precisely the value function minus some term. So this term is usually added. This is the tail regularization between the land policy and the base policy. So the base policy you can think of like some supervised parenting policy or some policy that produces grammatically correct sentences. This is my interpretation. So you want to fine tune the model, but you don't want to go too far. You don't want to over optimize. So that's why this time frame. Okay. So so this was used. Okay, so this was proposed. The original idea was proposed in 2017, and they used actually just deep reinforcement learning, but not language models. And so this was used for language models in the last 3 or 4 years. Then.
So what was the example here? Like, it's not for language model and for?
Yeah, just for like robotics, simulated robotics environment. So there, I think what they did was they sort human experts like just very short videos of robots, and then human experts say that this one is better than this one, and they'll use that for fine tuning. Okay, so then, so this is another method. It's called direct preference optimization, which has been quite popular like in the last year because they saw that you can actually eliminate the reward model mistake. And the idea is very simple. And what they observe is that you can write the reward, the optimal reward in terms of the optimal policy in this form. So here this beta log zero fix is some normalization constant. And the point is that now if we just substitute in the logistic model, so maybe you can put that. Yeah, so here, let's say you can write it as 1 divided by 1 plus e power r star x y2 minus x y1. And from the previous expression, if I just substitute this value of r star, this normalization factor cancels out. So you don't have to estimate it. So you get this entire probabilistic model in terms of the policy pi star. So you can totally eliminate the reward modeling. And what they say is that okay, you can just optimize this loss function. You can eliminate the reward modeling first. But this happens only for this one step contextual claims. For multi-step, it's still a problem. And yeah, so let me just wrap up. What we tried to do in the recent paper at ICML is just compare these two models for like very simple linear LTP. So if you're given a linear reward model of some dimension and soft policy class, then okay, so there are these two approaches to this. So can you say which one is better under which conditions? And okay, so this is a complicated model, but you can show that okay, so there are some regime when one is better than the other, and actually it depends on the representation. So yeah, let me just mention this top one. So here, okay, so this part is the tail divergence between optimal policy and the reference policy. This is unavoidable. So then you have some additional error between these two models. And so depending on the beta term, so you sometimes RLHF will be better, sometimes DP will be better. And then this third row is also important. So when your reward model is not exact realistic, meaning that one star cannot be represented in terms of dimension, then you get some additional approximation over here and also here. So you can come up with a scenario when one is better than the other. So yeah, so depending on the dimension and representation, so one can be better than the other. So, but we just did analysis for very simple linear models. So we don't know what happens if we have more complex models. Okay, so yeah, I mentioned with some ongoing work that I'm interested in. So one is RLHF with diverse preferences. So if you're interested, so this is a very nice survey paper where they show that, okay, so if you have multiple different types of preferences, then probably there is some scope to use ideas from social choice theory or voting for recreating this kind of preferences. So that's one direction I'm interested in. And also, like, if you have some kind of robustness or data corruption with this data, so how do you design a relative, or even like how to develop robust version of your relatives? That's the direction I'm interested in. Okay, so Jens, yeah, so this was joint work with Goran, Stelios, Bain, and Andy. So most of them are from Max Planck Institute in Saarbrücken, software systems and informatics. Yeah, that's where I did most of it. Thank you.
Questions from them?
Is the name supposed to be Nike or Nika?
Sorry. Oh, okay.
Yeah, so we can take questions offline. Debmalya is also around, so we can ask them then. Okay, let's thank Debmalya also.
Yeah, actually going to one thing and seeing what is, but this